iBot Club of IIT Madras, and today I would be giving you the insights about how to use computer vision in robotics. Before starting, we should know about what computer vision really is. So, in layman's language, computer vision is a field focused on enabling machines to interpret and understand visual data, which includes images, videos, and real-time camera feeds. Computer vision finds use case everywhere in today's world, including CNNs, autonomous vehicles, and medicine. So now we are going to set up an environment in our PC to make computer vision work out. Let's move into the PC. So here we are in our computer screen, as you can see. So the first thing we need to create is we need to create a virtual environment to do all the stuff related to CVI on that environment so that it doesn't hamper the other files. So first move into the terminal, you place command space and you type dir. So then we will get the terminal window. Then how do we create a virtual environment? I have Python 3 installed in my Mac, so I can type Python 3 minus m when and then the name of the virtual environment. I'm using as CV here, so it will create a virtual environment. Just wait a few times. Yeah, it's been created. Now how to activate that? So the code for that is source cv /bin/activate. So here I type and see there is before then my name and my username there has came some bracket CV which indicates that we are in the virtual environment. Now what we need to do is that we need to install the important files. So for testing CV against computer vision, we need to install OpenCV, which is the Python library used for like all this computer vision stuff. So how do we install them? Because I have Python 3 installed, so I would be using pip3 and you guys would be using pip or pip3 accordingly. So my code for that is pip3 install OpenCV Python. Wait a second. So you can see all of this libraries and its packages fetching, and now it's done. So now we will just create a Python file. Touch suppose your cvx.py, just you can name it according to you. So it just creates a Python file, and how to open that in, now we have to open that in VS Code. So the command for that is code cvx.py. So it will open this in the VS Code and we get into the VS Code window. Now we need to test whether CV2 is working or not. So we will just create a sample code and see just it's working or not. So for that we need to import the library which is named CV2, like OpenCV is named CV2 as a library. So we will just import that first. Import CV2 as no, not required, it's actually a very small name, so we can just use that name also. So now we will use like variable cap to capture the video frames which would be like from the camera itself, and the camera, how to capture that is cv2 dot video video capture, as you can see. And the code for that because I would be capturing the frames from my webcam, the code would be 0. Now we have to check whether it is reading the video like frames or not. So if it's not reading, that will show an error message, so we can debug it. So how to do that? So I will use a if statement, like if not cap dot im is open. So it's the function for checking that thing. Then we will use this colon, and then I will print a message, print that camera is not being open. So whenever it will like find difficulty in opening the camera, it will just show this error message. Then we will exit this thing, like it will just close the program. Now if it's true, like if this camera video open is true, then what we will do, we will just show the frames and all. No? So I am using the while loop here. while true, and now we'll use a while loop which is already assigned to true so that we can work it continuously. So now we'll assign two variables, ret comma frame, to the same thing, comma, sorry, my typo, frame equal to cap dot read. This function reads the frames. So now we'll check if it is able to grab the frame or not. So if not ret, then we will print another error message, print some normal basic error message, error, suppose error 404, which stands for not found, and it will then break. Shit. Then if it is not entering this loop, then we will directly use that, we will directly show the frames which it is getting input. So we'll use this function as imshow. So for activating this function, we have to use .cv2, which stands for the library, then imshow, then we will just name it live video, and for the object which we will be taking as input as frame. So we'll be just showing the live video frame. Now we'll be using something which is known as wait key to refresh the window every time. So how we'll be using it is using some if statement known as if cv2 dot wait key, and the argument for that is 1, which stands for 1 millisecond. It will be refreshing it like each and every millisecond, and 0 cross ff equal to or q, then break. Now what we need to do is that after the completion of the program, we should kill all the windows. For that, there are two commands, which is cap.release, and cv2 dot destroy all windows. So I guess it should work. We will save this file and then run. As you can see, like it is showing my camera feed to you all guys. So I guess I feel like it's working. So we are successful in setting up VS Code. So let's move to the new part. The next part of the video, where I will make you understand the basic concepts used in CVI in daily life. So unlike us, the computer perceives an image as a 2D matrix of pixel values that represents visual information. These pixels encode color and brightness at every location of the image. So we can see that in CVI, images are just data, just numbers arranged in a grid that describes what we see. There are various kind of ways where we can represent the image in. First way is RGB format. So what is RGB format? It is represented as a 3D array where each pixel has 3 values intuitively, which for red, green, blue. So each channel has value ranging from 0 to 255 based on the brightness. And other way is grayscale image. So grayscale uses a 2D array to represent the image, and each pixel has one value ranging from 0 to 255, like depending upon like the brightness of like depending upon going from white to black. Now we'll learn how to visualize and manipulate JPEGs and JPGs in computer vision. So let's see. So we are back in our computer. So I have downloaded one IITM image, which is the Himalaya MS of IIT Madras, and we would be using this JPEG image to manipulate various things. So first, what we are going to do is like we need to activate our virtual environment to do all the stuff. So I have created a new virtual environment named as comby slash then slash activate. So we have activated the virtual environment. Now in this folder I have already made one Python file with this virtual environment like characteristics named as image manipulate.py. So here we will be doing all this stuff. So let's get started. So first we need to read the image. For that we need OpenCV as a library. So what we'll do is like import cv2, which is the name of the OpenCV library. Then we will take a variable name as image img, which stands for image, equal to cv2 dot imread. You remember imread is the function for like reading the data. So what we are going to read, the JPEG image. What is the name of the JPEG image? It's named as iitmmensa.jpg. So we'll just write the name iitmmensa.jpg. So it will read the file. Now let's see whether it's working or what not. So we will use imshow to display the image. So cv2.imshow. You remember imshow we used while testing. So cv2.imshow image, and what with the name with which it's getting displayed, let's name it as image image. So then we will need to write the weight key and stuff. So for image display we don't need to refresh the window multiple times, so we'll keep the weight key as 0, as you remember. And then we need to close all the windows, cv2 dot destroy all windows. So then let's run it. It should work. Yeah, we are able to see the image of the Himalayas. So now what we were doing, we would be manipulating many stuff like converting into grayscale and all, converting a grayscale, then making a rectangle and just converting the whole block out of it to like green or something. So let's do. So first let's let know the insights of the details of this. So let us first comment it out. We can comment out using control slash, so all of the things gets commented out. So let's print about the details of the details of the like the dimensions of this in JPG. So for that we use a function named as img.shape. Sorry, shape. So let's see what kind of dimensions it has. It's not running over. Wait 1 second. So let's see. This shape outputs the height, the height and width of this JPEG image, which is 1200 pixels by 1600 pixels, and 3 stands for the type of image, which is JPG in this format. And we want to know about the details of the any part details of the any part of the JPEG image. Suppose for the first top left 5 by 5 region we want to know the pixel information, then we can just print it using print suppose what we are printing, top left details, left details. Let's keep it up to 5 by 5 like pixel density. So image, we are going for the like length and breadth. So length will go from 0 to 5 pixels, then breadth will go from 0 to 5, so 0/5. Sorry. So it should work, I guess. So let's save the file. Some details am I missing or not? Okay, there would not be any. Sorry, my bad. There would not be any closing brackets in between. So it should work now. Oh, I have made a typo also. Let's comment it out first. So you can see the details here in this part of the window, like it's showing all the pixel information. So the pixel information is represented as BGR values, which stands for blue, green and red, not as the conventional RGB values, because that's how CV2 works. So you need to be taking care of this thing in like while grayscaling the image. Let's learn now how to grayscale the red image. So we will make another variable known as gray, which we will use a function known as cv2 dot convert color, which stands for cvt color. Then we will use image as the argument. Then we will convert, use another type of thing known as convert color, cv2 dot color cu, it should be in capital, color and underscore. Then we will use from, we are going from RGB, which is BGR in cv2 format, to grayscale, right? So we'll be using BGR, sorry, my bad, BGR. 2 stands for 2, very intuitive, to gray. Now we will display this image. So we will display this image using imshow. So cv2 dot, sorry, imshow gray, comma, gray is the like argument, and what will the name above which it's displayed. Let's name this grayscale image, grayscale image. So then we will keep the weight key and all, cv2 dot weight key, and it should be 0 for that. And then we will use we will destroy all the windows using this one. That's the favorite part of me, destroy all windows, some kind of destructive things. So let's run. It should work most probably, and yeah, you can see it has been completely grayscaled. So we are successful in grayscaling the image. So what happens if we grayscale the image while analyzing? So if we want to perceive the depth and all, so we don't use RGB things directly. We first convert something into grayscale, and then only make the use of that grayscale frames to like work on depth and all. So that's why convert into grayscale is a very crucial part in like computer vision. So we will see the use case in like our upcoming sessions. So what kind of new manipulations we can do? Let's suppose we want to draw a rectangle, blue colored rectangle. So what we'll do in that case? So first let us replicate the image, is we don't want too small on this original one. So image, suppose you can have a rect for rectangle, as we are drawing a rectangle. So we will use rectangle equal to image dot copy. So it does what it stands for. It just copies the image stored in img to img rect. So what we'll do, we cv2 has a function named as rectangle, which is used for drawing the rectangle shape on overlaying over a jpeg image. So we will use this function. It is the code for that is cv2 dot rectangle. Then which image we are working on is image rect. We'll just use this thing, and what kind of, up till what pixels we are going to use. So we want to, so we can we can define a rectangle using two opposite diagonal points, because if you know the two opposite diagonal points, then you know how it is getting formed. Like length and breadth is, length is like this x axis of this minus axis of this, and breadth is ordinate of this minus ordinate of that. So if we have two diagonal points, we will get the information about the complete rectangle. So we will take the argument as two diagonal points. Suppose 50 comma 50 is the diagonal point, then another diagonal point, say 400 comma 400. So we are getting approximately 350 by 350. So it's becoming a square. So let us change the value to 200. So it is getting a some kind of 350 by 150 pixel sized square. So now we are supposed to make a blue. So we need to give the argument as 255, which is like the argument which is take is like BGR for cv2. So we need to input as like the depth values as 255 0 0, which is 255 brightness for blue, which is the brightest one, then goes green for 0, then blue, then red for 0. So that's why we are only getting the blue color, and after that to another argument. So then we will use cv2.imshow to display what we have done currently. So it should be a rectangle, comma, what which we are working on is image.rect, right? So then we will just use the arguments as cv2 dot wait key, and it should be 0 for displaying a static image. Then cv2 dot destroy all windows. I told you that's my favorite part. So let's see if it's working. Yeah, you can see that we have generated a blue 350 pixel by 150 pixel sized rectangle. So we can use this rectangle to like point out something on over the image, like up to a very good precision. As suppose we can also make things move, like move. Suppose we are detecting something, so we can border something out of it. So in that point, we will using this rectangle or maybe a circular thing also. So then for circle, it's like we have to define the center point and the radius. So in that way we will be getting a circle, and that would be some task of other day. So that's how we manipulate stuff. Now we can arise the question about how we do image processing. Image processing is done in a number of steps according to the necessity. Here I'm gonna discuss a few. So the first comes blurring. As it sounds, it is used to blur and reduce image details by filtering neighboring pixel values. It is mainly done to simplify image for analysis. There are three general algorithms used for blurring, which are Gaussian blur, median blur, and box blur. We'll get into the details of all of those. So first comes Gaussian blur. Gaussian blur is the most commonly used technique in image processing for reducing noise and details. So why do we use it? We generally use it to reduce image noise before edge detection or contouring. The Gaussian blur algorithm uses the following formula to do so. So there might be a question in your mind that if you want to analyze something, why do we need to blur the image? So what's the main intuition behind it? So here we can see that. So let us imagine that you are looking at an image through the frosted glass. You can make out the shapes and fine details even if it's blurred, right? So it significantly reduces the computational requirements used in edge detection, and that's why we use Gaussian blur before using that. So let's just dive into our computer to see the practical implementation of Gaussian blur. So guys, here we are back in our PC and we are going to implement Gaussian blur by, as you remember the photo which we imported last time, the IIT MNC. So we are going to make a blurred image out of it. So how we are going to do it? We are going to use Gaussian blur for that. So let us go to image manipulator py. So I've already, as you can see, I've already imported cv2. So we can directly read the image as like let us take a variable, suppose img. Then how to read the variable? So we remember imread as the function. So then cv2 dot imread, and the name of the file, which is itm mensa.jpg. So we have read the file now. So let us take a new file, a new variable name as blur to implement the Gaussian blur for that. So we are going to use a function name as Gaussian blur only. So very intuitive. So Gaussian blur. So what are the parameters now for implementing Gaussian blur? So for knowing the parameters, we need to give the image on which it is being implemented and the kernel over which the over which the image would be blurred around, and the sigma value which you are going to take. So how does a kernel work? A kernel is like n cross n matrix and is usually taken as a odd integer. So how it does, like whenever we have a image, it is just a pixel n cross n matrix, right? So what the kernel does is that it moves through that n cross n matrix which we have taken the kernel initialization as, and it takes the average of all the pixel values and puts uh, replaces all of the pixel values with that average value. So what we can see that if in a small in a small pixel area, if it is replaced by an average value, then we can see that the kind of blurring is happening. We can imagine that. So let us do that only. So image comma, then the kernel value, kernel size. So let us keep it 7 by 7 to keep it more blurred. and then the sigma value. So there is a code called 0. If we take 0 as the input, then the computer itself implements the sigma. So it decides where to keep the sigmas high, where to keep the sigmas low. So now let's print that, like show that. So how to use that is cv2.imshow, then blur, and what should be the name? Blurred Himalaya, suppose. Then the name of the blurred image, blur. Then what we are going to do is that we have to kill all the windows, and we have to keep the wait key also, as you remember. Then cv2 dot destroy windows. So it will be showing you the blurred image, I guess. So let's see whether it is working or not. As you can see, it uh, it is giving a very blurred image as we if we compare it with the original one. So where is my original one? Here's the original RTM Mensa. So as you can see, if we overlay one over another, then you can see that the pixel, like it's very like really visible, that Himalaya lettering and all. So how can we increase the blur? So the blur, how much blurred it is will depend completely on the kernel value. And so let's increase the kernel value to test. So suppose keep it 11 by 11. So supposedly it would be giving more blurred value. So let us run now. As you can see, like it is getting more blurred. So we are successfully implementing Gaussian blur. Thank you. So median blur is very similar to Gaussian blur, but the only difference is there. Here we replace the pixel value with the median rather than the average, or weighted average, which we are using in Gaussian blur. So finally comes the box blur. So the way in which box blur differs from Gaussian blur is that in Gaussian blur we take the weighted average of the intensity values of the pixels. So the weight is like something which is more higher in the center and lower in the corners and edges. So and while in box blur the weight is one for each and every uh, pixel. So generally it is the average, and the Gaussian blur is the weighted average. So guys, here is a quick implementation and like how we will find the difference between median and Gaussian blur and box blur. So I have written code which implements both, like all of the three: Gaussian, median, and box blur. So you can see that in median blur we only require the only since the kernel is a n cross n matrix, so we just need the n value for that in the median blur. And for box blur we get the similar argument as compared to Gaussian blur, but there is no sigma value. So let's run and just see what is the difference between all the three blurs. So I'm running this over a 11 by 11 kernel. So first we get the box, and then we get the median, and then we get the Gaussian. So let's decrease the image sizes a little bit so it's like more properly visible. Here we go. As you can see in the median blur, it's more like a painting, and box blur is like the most proper blur, as you can see, because it's like, and Gaussian blur, it still retains all of like most of the part of its like details and all. So I can see that if gosh all of the three are very useful depending upon the use case scenario. Next crucial part which comes under image processing is edge detection. As it sounds, edge detection is the process of finding the edges of a target body by calculating the sudden intensity changes in the image. How do we do it? So basically we have two algorithms to implement edge detection. One is Sobel edge detection, another is Cannet edge detection. The Sobel edge detection algorithm is basically a gradient based algorithm which calculates the change in intensities along x direction and y direction and then overlays one over another to get the best image. So guys, we are back in our computer screen to see the implementation of Sobel algorithm. So what we are going to do is that we are going to take this JPEG image of me, and just trace out the boundaries or edges of like the main figure. So I have the code here, so no need to write and see. So what I'm going to explain you the code here. So first we are reading my JPEG image, and we are converting it into grayscale, and we are not directly converting, we are just reading it as in grayscale format only, so it's much more easier. So it is one of the requirements of that Sobel function which we are seeing here. So then we are detecting the uh, edges in x direction, y direction using the command cv2.sobel. Sobel is the function here, and its parameters are image, like in the source image. Then cv2.c is something known as the d depth. So it will vary if you from cv underscore 64f to cv underscore 32f if you want to preserve the like negative derivatives also. And this is the dx or dy, like how many times you need to like derivate of that, derivate the values. So for x-axis we are only calculating a lot for horizontal edges, so we are keeping the uh, derivative as 1, and for vertical is as 0. And similarly for calculating the vertical edges, we are keeping the horizontal one 0 and vertical one 1. And k size is the size of the kernel which move over the image to calculate the derivative whatsoever. So the kernel's k size is 3, means it's a 3 by 3 kernel. And now you remember that the size of the kernel should be some always n cross n, and n should be odd, so keep in mind. Then we are combining both of the Sobel values, Sobel images, and getting the positive, like the highest magnitude values of these. So we are using cv2 dot magnitude to get the like edges for that. And after that we are showing the normalized values of um, the combined to get, because when we are taking magnitude it may also include the negative values, and the imshow function always require a positive value of intensity, so we are normalizing it by Sobel combined by Sobel combined on max. And after that we are displaying it, and the weight can destroy all functions. So let's see it's working or not. So you can see that we are getting a pretty like precise edges, even like this part where there is very little gap between me and the sea water, as you can see. Let me show you. Where is one input? Okay, so as you see, like here is a very small gap between me and the sea water, but it's still like able to detect this part. So like I feel like it's very useful in that case. So yeah, we are successfully implementing Sobel algorithm. Unlike Sobel algorithm, Canley edge detection is a multi-stage edge detecting algorithm used to give more accurate result. It implements Gaussian blur, gradient calculation, suppression, and thresholding to give more accurate values. So here is formal way of defining the difference between both. So here is a side-by-side comparison of Canny edge detection and Sobel edge detection. So I would be taking the edges using both of the algorithm on the same image. So let's see how it comes. So we can see that like for Sobel edges, the edges are really smoothened out as compared to Canny edge, but you can see that like Canny edge detection is missing on like the non-useful details like the edge of the sea. And also I feel like Canny edge detection is much more useful in like pointing out an object over a like layout of very different types of objects. So yeah. Next in the line of image processing come the step of masking. So what is masking? Masking in layman's language is something, what we do is that we take a stencil paper, place it over the image, and highlight the important parts which are known as the region of interest, so that it can be analyzed further easily. So we use two different methods to do masking. The first one is thresholding and the second one is bitwise masks. We'll get into the details of all in the implementation. So here we are back in our computer screen to take the implementation of masking using thresholding. So here I have written the code. So let me make you understand this one. So first we are reading the JPG. After that we are converting it to grayscale. After that we are using threshold function predefined in CV2 library, which takes the input as gray for the grayscale image, and this 0 is the this 100 is the threshold value which it would be taking as input. So what happens is that if the intensity value of each pixel is greater than or equal to 100, then it turns that pixel into 255, then which means highlighting that point. And CV2 thresh binary is like convert using it a binary function to implement this one. So what is that underscore? So this function has two outputs, one which is not useful and one is the masked output. So we are to ignore the first output, we use that underscore. After that we are using foreground to like make the mask more visible using colors and all. So let's see what kind of output we get. So here is the side-by-side comparison. This is the original one. Then as I said you in the description that it is like a sketching the most highlighted parts of it. So it is the sketch and it is the overlaid part, so it also kind of look like a colored sketch. So this thresholding is used to highlight the like object over a like very dense environment, so that it's like easy to detect and all. That's it. So we have learned various things in this session about image processing and how to perceive an image in the computer. Now to conclude this session, I want to give you a task of implementing the bokeh effect or the portrait mode effect which we use in our cameras in daily life. So it can be done using all of the discussed algorithms till now, and if you want you can just search for the internet to find some more useful aspects. So we will meet in the next session. Till then, goodbye.